Okay, wish me a little bit of luck on this one. It's a big problem. We're going to try to factor x to the fifth minus 7x to the fourth plus 11x cubed plus 25x squared minus 80x plus 50. So a fifth degree polynomial given that 1, 0 is 3 plus I. So by the complex conjugates theorem, we do know that 3 minus I will be a 0 as well. But one cool technique we can use is that if we know that 3 plus I is a 0, then we can attempt to solve this for, we know it's a 0, then we can write down x and solve this mini equation for the polynomial that has roots of 3 plus I. To do so, subtract 3 from both sides so that I equals x minus 3. Then square both sides, and I squared is equal to negative 1, and x minus 3 squared is x squared minus 6x plus 9. And then simply add 1 to both sides so that 0 equals x squared minus 6x plus 9. And this particular quadratic will have zeros of 3 plus I and the guaranteed 3 minus I by the complex conjugate theorem, since all of the coefficients are real. Okay, so there's 2 of the roots, 2 of the zeros. Now I'm going to take that and I'm going to long divide our original fifth degree polynomial by 6x squared minus 6x plus, whoops, I made an error there, didn't I? 9 plus 1 is actually 10. So I'll correct that. 9 plus 1 is 10. I only caught that because as I came over here, I was like, that's a perfect square. So now it's not a perfect square anymore, and we can long divide. Okay, so x squared going into x to the fifth would be x cubed. Multiply would give me x to the fifth minus 6x to the fourth, and then plus 10x cubed. Subtract, that one's gone. This one will give me a negative x to the fourth, and 11 minus 10 is 1x cubed. And then I'll carry down the next piece for a plus 25x squared. To get the negative x to the fourth, I'll need to introduce a minus x squared. Let's see, that creates negative x to the fourth. Distributing gives a plus 6x cubed. And then multiplying here will give me a negative 20x squared. Not negative 20, negative 10. Oh, I'm full of errors today. Negative 10x squared, so that when I subtract now, a little bit of cancellation, 1 and then 1 minus 6 is negative 5x cubes, and then 25 minus negative 10 would be plus 35x squareds. So now carry down the negative 80x, and it looks in the next spot that we'll have to introduce a minus 5x. So minus 5x cubed, then plus 30x squared, then minus 50x. And so that when we subtract now, we end up getting 5x squared. Negative 80 minus negative 50 would be negative 30x. And then our last spot down would be plus 50. So of course that on the end would be a plus 5. 5x squared minus 30x plus 50, and there is no remainder as expected. Okay, so now we have this factor and this factor, the red factor and the blue factor. I'm going to pull those over onto the next page so I can continue with the factoring. Okay, our red factor was x cubed minus x squared minus 5x plus 5, and the blue factor was the quadratic that gave us those 2 complex solutions, the 2 with imaginary pieces. That was x squared minus 6x plus 10. On the red, I'm now going to use the rational zeros theorem to determine if there are any rational zeros, or what the possible rational zeros are, so that we can play with those. The factors of 5 are 1 and 5, and the factors of 1 are 1. So the only possible rational solutions would be plus minus 1 or 5. Okay. I will test out the number 1 the 0 of 1. So 1 into 1x cubed minus 1x squared minus 5x plus 5 would yield 1. 1 times 1 is 1. 0. 0 times 1 is 0. Add is negative 5. Multiply. And there's 0. So that means now the red factors down into the x minus 1, because that's the root that we were proposing, the 0 that we were proposing, and the residual, which is x squared minus 0x minus 5. Okay, so now I'm going to come to the next page. Let's see if we can fit it in here maybe. So let's cut that off. We have the red, which is now factored down into the green, yielding x minus 1 and x squared minus 5. And then we have our blue piece, which is x squared minus 6x plus 10. Now notice that the x squared minus 5 is not going to factor any further over the rational numbers, because of course the two zeros of that one are plus or minus radical 5. The blue is not going to factor down any further because, as we discussed at the beginning, those are complex solutions. So if we were tasked with finding a rational factoring, a factoring over rational numbers, this would be a rational factoring, because all of the pieces, we can't break down any of the pieces any further without allowing more complicated numbers. For example, more complicated numbers, we could expand into the reals, and x minus 1 would be a factor. We could now take our green x squared minus 5 and turn that into x minus radical 5 and x plus radical 5, because those are also real numbers. They're not rational, but they are real. The blue piece, however, that cannot break down any further, because remember, those solutions have imaginary pieces to them. So what's the next level of numbers? That would be complex. If we allow complex numbers, then we do allow those imaginary pieces, and so now we could factor into x minus 1, x minus radical 5, and x plus radical 5. And the blue would further break down into x minus, and the solution that we were given at the beginning was 3 plus I. And then the other solution by the complex conjugate theorem must be 3 minus I. So this would be a complete factoring over the complex numbers. If we were tasked with only finding the zeros, if the command was find the zeros, then you would have the same, you'd have to go through these same stages, but your conclusion would now be that your zeros are 1, then you have a radical 5, then you have a negative radical 5, and then you have your two complex numbers, the 3 plus or minus I. Well, I guess all the numbers are complex, but the two complex numbers with imaginary pieces.